Good afternoon, everyone. Okay, so today we are going to continue with uh, the core. Um, I would say the core content of this course. So, which is Coulomb's law and electric field, electrostatic field. So, yesterday I mentioned there are two field. I mean, two fields of study in electromagnetics. So one is static and one is dynamic. Of course, we have to study the static first before we move to the dynamics. So for electrostatic, uh, we deal with charge at rest or stationary, or we call static. That's why the name static. So 1 coulomb is equals to 6 times 10 to the power of 18 electrons. And fundamental quantity of charge in a single electrons is just Q times number of electrons and the electron charge. So the electron charge is just is equals to negative 1.6 times 10 to the power of negative 19. So in atomic physics, positive charge is related to proton, while negative charge it is referred to as electrons. So Coulomb's law is, it is found by experimentally uh, determine uh, the laws. So charge are never can never be created or destroyed in an isolated system. So therefore, we have conservation of electric charge, and same as goes for conservation of energy. So there is a few distribution of charge. So one is point charge. So the distribution is at a point, yeah, at a point. So we have line charge, then the distribution is over a line. Surface charge, that means the charge distribution is over a surface. And of course, volume charge is it is distributed over a body, a surface. So Coulomb's law, hypothetically, it deals with the charges between 2 points. So between 2 point charge. So the subsequent expression derive that we can derive from Coulomb's law, it is the electric field and also the electric field intensity, which is E. We refer it as to E, the electric field intensity, and also the electric flux density, D. Okay, and of course, subsequently, E and D is related. So Coulomb's law, if let's say we deal with charges, uh, light charges repel and unlight charges attract. Okay, so the strength of the force, basically we use Coulomb's law to calculate the force between two charges at a distance. So the force, indeed, it is proportional to the product of the charge and inverse proportional to the square distance between them. So the formula, so so the proportionality just now, I mentioned just now, the proportionality that I mentioned just now is the force, the Coulomb's law between two charge is directly proportional. So the proportionality is directly proportional to the, so this is the proportionality relation, the proportionality symbol. So we write it as the product of two charge and inverse of square distance between them. So that means if let's say you have a point charge at Q1 here, and it is at a distance of R from Q2, then the force between them, okay, the force between them, let's say assuming that this 2-point charge is positive, so the force exerted from one charge to another, or from Q1, the force exerted from Q1 to Q2, or the force exerted from Q2 to Q1, it is governed by this proportionality. So this proportionate, so in order to make this law, or the formulation valid, so there's a proportionality constant K, which is shown here, K. And K is 1 over 4 pi epsilon naught. And okay, for now, we will take that epsilon naught. We call this as permittivity of free space, or free space. Okay, so free space means we refer it to vacuum. Normally we refer it to vacuum, and it's very close to air. I mean the medium surrounding us, the air that we breathe. Okay, so it's very close to the permittivity of free space. So for now, we will assume that epsilon, we should write this, perhaps we should write the proportionality constant K as, this should be written as K is 1 over 4 pi epsilon only. So we will discuss further, and this epsilon, by right, in general, epsilon is actually epsilon not epsilon r epsilon naught. So this epsilon naught is referred to relative permittivity. Relative permittivity. So it is actually the referring to the scale, or because for different medium, we have we were able to obtain the relative permittivity of the medium. So for, let's say, some material, so we have a dielectric material. So we have different dielectric material, we have different relative permittivity. So for example that I can give you is polyethylene, which is a dielectric material. So when I mention dielectric material, is somehow is related to insulator, like rubber or plastic. They have different type of relative permittivity. So of course the permittivity itself of the material, we have to calculate the relative permittivity multiply with the permittivity of free space. So the epsilon naught, normally I will use this relation. So which is much easier to remember. So it's 1 over 36 pi times 10 to the power of negative 9. And of course, if you use calculator, um, if you use a constant, if you type in constant 32, shift constant 32 in your calculator, the value of this, the value coming out from the calculator in constant, referring to constant 32, is different from, I mean, it's slightly different with the value of 1 over 36 pi, but it's good enough. The value is the value. I mean, there's a small error. It's a very small error. So the approximation is good enough with 1 over 36 pi. So I mean, unless you remember what is this constant 32 referring to, otherwise I will just remember this value 1 over 36 pi times 10 to the power of negative 19. That is referring to the permittivity of free space. So here earlier we only calculate the magnitude of the force, So how, if you want to relate to the direction of the force, and this have to do with the location of this point charge, the location of the point charge. So the location of the point charge have to be given for, let's say for example, Q1 and Q2. The location of the point charge have to be given in three-dimensional space, x, y, z. So for example, this is I call that, let's say Q1 is x1, y1, z1. The location is here, and the location of Q2 is x2, y2, z2. So in vector, in matrix notation, this is a vector. And how do we calculate the unit position vector A1? How do we calculate this? The unit position vector of A1 in a direction, in the position vector from this point to this point. So basically, in general, I will first, I mean, this can be actually rewritten as Q1, Q2, 4 pi epsilon naught r cubed r. Okay, so where r is A12, okay, in this vector here. Okay, I mean the vector that the position vector that that we refer to this diagram, that connecting from Q1 to Q2. So how is it I mean, how do I rewrite this? Because bear in mind the unit vector here, cap, is equals to the vector A12 divided by the magnitude of A12. Okay, this is the unit vector notation. Or maybe I can write this as R over magnitude of R. Okay. Oh, yeah. So of course this R squared here, there's no arrow on top, so therefore it is the magnitude. This is referred to the magnitude. So if you wonder whether this is a magnitude or not, so normally I will put magnitude as this, a modulus, and inside the modulus there is a symbol, the vector symbol. So that represent the magnitude. Okay, so so how do we relate? the vector from here to here, let's say from A12. So the direction is, the vector direction is pointing from Q1 to Q2. Yeah. So A12 referring to the vector pointing from Q1 to Q2. So this refer to x2, y2, z2 minus x1, y1, z1. Otherwise, if it is A21, that means the vector pointing from Q2 to Q1. So this is x1, y1, z1 minus x2, y2, z2. Okay. Otherwise. Okay, so once we have established this vector here, then we can, once we know this vector, then subsequently we can calculate the magnitude of the vector. Okay. All right. So if F12 is pointing from, I mean the force if it is referring to the force exerted from Q1, from the charge Q1 onto the charge Q2. So is equals to is equals to this formula, and it is equals to the negative of the force exerted from Q2 to Q1. So this negative here is just the polarity. I mean it's the inverse of this, right? So if you look at A12 and A21, so here we can see that A12, that I mean the direction, right? So here we can see that A12 is equals to the negative of A21, right? So that's the reason. That's the reason why F12 is equals to the negative of F21. So bear in mind, um, if you look at, this is the vector notation. So we are dealing with vectors. So therefore there's a direction. And of course the magnitude is the same for forces. Okay, let's try one example. um, 4 charges of 10 microcoulomb each are located in free space at -3, 0, 0. So this is coordinate system given, Cartesian coordinate system. And another one is 3, 0, 0, -3, 0, 0, -3, 0, and 0, 3, 0. So if we observe carefully the location of these 4 charges of 10 microcoulomb, it is located on XY plane. It is located on XY plane. So because the value here is XY Z, right? -3, 0, 3, 0, 0, -3, 0, 3. So it is located on XY plane in Cartesian coordinate. So find the force of 40 microcoulomb. Find the force exerted by this 4-point charge located at a distance at which is located at 0, 0, 4, at a distance 4 unit above the XY plane. So if you want to view this, so this is the 3-dimensional view. So I will write this so that I will write the location so that you have reference on this. -3, 0, 0. So this is 3, 0, 0, 0, -3, 0. Here is 0, 30. And this point here is 004. And Q1, so I will write here Q1 equals to Q2 equals to Q3 equals to Q4 is 10 microcoulomb. And the Q at position 4 and Q at position 4 is 40 microcoulomb. Okay. So now I want you to find the total force experienced by Q at this point. So I want to find the total force experienced by Q at this point. So I want you to try to calculate this. Okay. So based on the formula, so I have shown you how, I mean, you should know by now how to calculate the vector from one point to another point. So this is the force exerted by each point charge. Q1, Q2, Q3, Q4 exert the force on Q at this position 004. So I want you to calculate the total force, the net force experienced by this Q. So I will write the formula as well. In general, so we have Q and 4 pi epsilon naught r cube r. So bear in mind the r cube here referring without the arrow is referring to the magnitude. Okay, so please try this now. So we time ourselves, say 10 minutes for this. 10 minutes. All right. So first, um, what we need to do is to find the vector. So representing the force uh, exerting from the charge Q1, Q2, Q3, Q4 respectively towards Q, towards Q. So so I will represent this vector here as R12. So R1, then this is R2, R3, and R4. Yeah. So first, what I need to do is I need to find what is R1, the vector R1, and R2, then R3, and finally R4. Okay, so now once we obtain all of this, so here we can see that the magnitude of R1 is equals to the magnitude of R2. So because the value is the same, right? The value. So the magnitude of R3 and equals to the magnitude of R4. So which is the square root of 3 square plus 4 square, which is 5. Okay. And the product of each charge is also the same. The product of each charge is also the same because Q1 is 10 microcoulomb, here is 40 microcoulomb. So the only things that is different is the vector. Yeah. The direction of the force that is pointing from Q1 to Q is different with Q2 to Q and the rest of the charges. So now we establish the force. So so F1 referring to the charge Q1, the force exerted by Q1 to Q. So it is 10 microcoulomb, 10 times 10 to the power of negative 6 microcoulomb, and 40 microcoulomb divided by 4 pi epsilon naught. So epsilon naught is 1 over 36 pi times 10 to the power of negative 9 R1 R1 cubed. So R1 cubed, just now we have found that it is 5, so therefore it's 5 cubed, 5 to the power of 3. And the vector of R1 is 304. So I can write this as 3x cap plus 5z cap. Okay. So let's count this. Let's calculate this. The term. Let's calculate the term of the square root bracket term. Yeah. Sorry. The square bracket term. Let's calculate the square bracket term. Okay. Okay. What about f2? So f2 will be the same. So the square bracket term will be the same. Yeah. So I will remain at 0. I will just write 0.0288, and then the vector is only different. The only different is the vector. So it's -304, right? -304, and I can write this as -3x cap plus 5z cap. And similarly, f3. 0 FR3 is 034. 034 is 3y cap plus 5z cap. And F4, then it's -3y cap plus 5z cap. Okay. So therefore, the net force experienced by charge Q is therefore the sum of all the vectors at that point. So we add all this. So we can see that the -3x and positive 3x and -3x cancel off, right? Someone texted me. Just let me see. Four Z, is it 4Z or 5Z? Check again. It is located at, oh, sorry, yeah, 004, sorry. Yeah, 004, sorry, my mistake. Okay, so now, so we are going to sum all the forces, So here we can see that the negative component of x in F1 and F2 will be cancelled off, right? If we add F1 and F2 together. And similarly, F3 and F4, the y component will be cancelled off. So this gives us as 1, 2, 3, 4. So it's 4 times 0.0288 multiplied with 4z. So this will give us 0.46 z cap. So that means the force, the net force, it is pointing in the direction of z. It is pointing in the direction of z. Another perspective that I want you to look at is, if you look at the location of the charges, so they are symmetrical. Yeah. So what I'm saying, what I'm trying to tell you is, let's say this if you look at this diagram here, okay. So I'm going to draw it in a different point of view, so you understand what I'm trying to tell you. So I mentioned symmetry. I mentioned the word symmetry, right? Okay. Let's say now I draw this diagram here. A two-dimensional view instead of a tree. So let's say this is z-axis, and this is x-axis. Okay. So this is Q. Let me see. Q1 and Q2. Okay. So this is Q1 and Q2. So that means, if I'm looking at the direction of y-axis, that means I'm looking, if let's say you stand here, so let's say you stand at this point here and look straight here, look straight into this direction, look straight into the negative direction of y. That means you're looking straight at here, so you can see that this is the axis now. So Q1, Q2 is here, so this is 0. And now, without stating the coordinates, so I will draw the force. I will draw the electrostatic. The electrostatic force that passes through, that is exerted by Q1 and Q2 at this point. So this is the point. Yep. So this is F1 and this is F2. Okay. Okay. So from this diagram, I will redraw again, only showing F1 and F2. So F2 and F1. So bear in mind, the distance from the origin to Q1 and the distance from the origin to Q2 is the same. And therefore the forces, the direction of the forces is also symmetrical about the z-axis. So if you look at the symmetrical point, So I'm sure now you should be able to know, if let's say if I give you a angle here, then you can now decompose the vector into the vertical component and also the horizontal component. So let's say now I decompose F1 and F2. So F1 here, so I will draw this slightly here, slightly over here, which is, let's say, F1 vertical component and F2 horizontal component. So I put a subscript here, the index H and V, just to represent the vertical component and also the horizontal component. So same goes for F2. So there's a vertical component and also there is a horizontal component. All right. So from this diagram, you can see that since F2 and F1 has the same magnitude, yeah? So it has the same magnitude, but of course in a different direction. But due to the symmetry location of the charges, we can see that these forces cancel off, right? These forces cancel off. So these forces cancel off. So that means if we try to decompose the forces into horizontal and vertical component, so here we can see that the horizontal component cancel off. So only the net force here is the only net force here is only the vertical component. So we can do this analysis. Same goes for Q3 and Q4, right? Um, so let's say I draw this. Okay, same goes for Q3 and Q4. The location of Q3 and Q4 is also symmetrical. And again, we have the similar situation. If we try to resolve this, so okay, so the justification here now is the same. Since both Q3 and Q4 they are spaced equally with respect to the z-axis, they are spaced equally with respect to the z-axis, and also they have the same charge. Yeah, they have the same charge, and therefore the forces, the force exert on Q will have the same magnitude, but of course the direction is different. So from this diagram here, again we will cancel off. The horizontal component will be cancelled off. The reason why I'm telling you this, because in a subsequent discussion, in our subsequent discussion for electric field, it is important to note the symmetrical distribution of charge. That will reduce our work a lot more. So in this case, if let's say if I notice about, let's say if I notice about the symmetrical distribution of the charges, so I do not have to compute. I do not have to compute this basically. So straight away, I just look into this. That means I do not have to write this down. Of course, this is just a minor, some minor reduction of the work, but in the subsequent discussion about electric field, we are you can see the significance of the complexity that we are going to deal with. So that if let's say we not we uh we recognize if we recognize the symmetrical charge distribution, the calculation of the forces will be much easier. Okay. I think we have to stop here. So we have a few minutes more. I need your help, actually. I need to check with you. Is there any slot that I can use uh, to replace, not to replace, to change the sorry. Let me address this first. Okay, I rechange is 4z. Don't need divide by 5. Oh yeah, Mawad Adin, you're right. Because I have written it as r cube. Yes, correct. Okay. So as I come back to what I want to tell you is, I wanted to change the class for today because some of the repeat student who want to enroll to this course, so I need to change the today classes to another slot. So can I check with you? Is it possible that we change it to Wednesday? Is it possible that we change it to Wednesday? Let me check here. Okay, is it possible that we change it to Wednesday? Anytime before 1. Anytime before 1. Just wait on. Just let me confirm something. Just let me confirm something. Sorry about that. Just let me confirm something. So possible for me to change 9 to 10 Wednesday? Or we can also do Thursday if possible, if you want it. I mean, if it's so I have a good timing for Wednesday and Thursday, or we can move earlier to Friday. So maybe you let me know Wednesday, Thursday, Friday slots for you. Before noontime, before 12 is the best. Give me some some info whether is there any suitable slot that you can accommodate for Wednesday, Thursday, and Friday. So Wednesday anytime before 1, Thursday anytime before 2, Friday anytime before 12. So please let me know. Friday morning. Okay. Mm, okay. I think the other student Friday cannot. I think. Yeah, I think the other student Friday cannot. Because Friday starting from 10, 11, 10 to 11, 11 to 12, 2 to 3. So I have a class at 12, starting from 12, unless I start at 9 to 10. Okay. Um, 9 to 10. All right. Okay. All right. Thank you. Thank you, everyone. So I will check. Yes, if it's effective, then it will be shown in your intranet timetable if it's effective. So today I'm just checking with the main cohort. I mean, checking with you so that I can accommodate this the two students that want to repeat the course. So if they are okay, then confirm. Then the changes will be effective next week. All right. Thank you, everyone.